Good morning, everyone, and welcome to day one of our online classes. I had asked you to review lessons 1 through 8 for the circles module, and today we are going to start with lesson 9. Lesson 9 talks about the properties of tangents. So you should have a cheat sheet with all the theorems and all the important facts about circles that we have learned so far in lessons 1 through 8. Now, when we start looking at tangents, first we will start looking at some vocab and understand what a tangent is, what a secant is, and other theorems that are related to tangents of a circle. So let's start with the definitions of tangents and secants. A tangent to a circle is a line in the same plane that intersects the circle in one and only one point. So it's important for us to understand that this is a tangent is a line that is completely outside of the circle and touches the circle in one and exactly one point. So it looks something like here is a circle with center O. So a tangent is a line that is going to touch my circle at exactly one point P. Moving on to a secant to a circle. A secant to a circle is a line in the same plane that intersects a circle in exactly 2 points. In exactly 2 points. So a secant to a circle looks like, here if I have my circle again with center O, a secant is a line that is going to touch my circle in exactly 2 points. I'm calling these points X and Y. So here is a tangent to a circle and here is a secant to a circle. Both of these are lines and not line segments. Both of these are lines and they are touching the circle in one place where we are calling it a tangent and in two places when we call it a secant. Next we come to an important theorem for tangent to a circle. So tangent lines are perpendicular to the radius of a circle at the point of tangency. What I mean by that is if we have a circle with center O and I have a line L and the point of tangency is this point X. So I'm calling this point X. The point of tangency is the point where the circle touches the tangent line. So the tangent lines are going to be, so if I draw a radius to this point of tangency, I drew this radius R to the point of tangency. It is going to be perpendicular to my tangent line at the point of tangency. That is what I'm trying to say. So at this point, I want you to pause the video and go to resource 1 that I have posted on the Google Doc to review and get more used to these terms and this theorem that we have just seen. So please pause the video now, go to resource 1 for Wednesday, for the same day that you're watching this video for. And there are some exercises that you can do to familiarize yourself with these new terms and this one theorem that we have learned so far. Once you're done with that, come back and start watching the video again. Okay, moving on. Now, I am asked to prove that if CD and CE are tangents to a circle A, so I have a circle with center A, and I have these tangents CD and CE are two tangents to the same circle. They are asking me to prove that A is equal to B. I am going to give you a hint, and then I want to see if you can prove this by yourself and write a 2-column proof to prove this. I need a 2-column proof. So the hint I'm going to give you are the constructions that I'm going to do here. The construction is going to be, I am going to draw a radius AD and AE. So draw radii AD and AE. Also, I want you to join points A and C. So we are going to join points A and C. I hope you can all see two triangles. Use these two triangles to prove that A will be equal to B. Write a 2-column proof for me. So pause the video, go ahead and write a 2-column proof. Okay, here is my 2-column proof. I know that because CD and CE are both tangents to the circle A, they are going to meet my circle. The radii and the tangents are going to be perpendicular to each other. So these two angles are going to be 90 degrees. I'm going to call them angle 1 and 2. So angle 1 will equal angle 2 will equal 90 degrees. And this is because tangent lines are perpendicular to the radii at the point of tangency. It's very important for us to remember that this will only happen when the radii and the tangent lines are meeting at the point of tangency. Okay. Having said that, I can also say that AD is equal to AE, and that is because they are radii of the same circle. AC is equal to itself because of the reflexive property. So therefore, triangle ADC is going to be congruent to triangle AEC. C using the HL criteria. So then CD should equal CE because corresponding parts of congruent triangles are congruent, CPCTC. So here is your proof. So here, what I have proven, I have given you another theorem. And this theorem, okay, let me write it here only. The theorem says that two tangents to a circle from an exterior point are congruent. So from any point on the exterior of the circle, so in this case the point C, which is in the exterior of circle A, I can draw two tangents to the circle A, and these two tangents are going to be congruent to each other. They are going to be equal to each other. Okay, moving on to the next page. I am now given a circle A, and the radius of the circle is 9 millimeters, and also I'm given that BC is 12 millimeters. So BC is 12 millimeters, and the radii, so I can draw the radii. This radii AB is going to be 9 millimeter. They are asking me to find AC. They are asking me to find AC. Now, remember the important fact that the radii and the tangents are going to meet each other at 90 degrees. So, pause the video and go ahead and find the length of AC. Okay, when I found AC using the mother of all theorems, I can see that AC square will equal AB square plus BC square. When I plug in the numbers, I will get this is equal to 12 square plus 9 square, so which is 144 plus 81 to give me 225. So that tells me AC is going to be square root of 225, which is 15 millimeters. To find the area of triangle ACD, I know area of a triangle is 1/2 base times height, and you can pause the video and go ahead and do B and C also on your own and come back and check your answers with my answers. So plugging in the numbers, I got the area to be 54 millimeters square. Now I need the perimeter of quadrilateral ABCD. So I can make the quadrilateral ABCD, and I know AD is going to be 9 also because this is the radii of the same circle, and CD is going to equal CB because from an exterior point, when I draw tangents to the same circle, my tangents are equal in length, and these are the radii. So the perimeter of this quadrilateral is going to be 9 plus 12 plus 12 plus 9, adding all the sides, which will give me 42 millimeters. Okay, let's look at the next problem together. Number 3. I have a circle A and EF. Let me just make all these a little bigger. Okay, so EF is given to be 12, AE is given to be 13, and the ratio of AE to AC is 1 to 3. So that tells me my AC, because AE is 13, AC is going to be 3 times 13, which is going to be 39. First thing they want me to find is the radius of this circle. So I am going to draw this radius AF, and that is what I am trying to find. Now, if you think you want to try this on your own, go ahead and pause the video and do this problem 3 on your own. If you are stuck, you can follow along with me. Okay, so because EF is 12, this is also going to equal ED because of the theorem that we just saw. So this is also 12. And this is given to be 13. And I know these tangent and radii are going to meet at 90 degrees. So to find AF, my AF squared is going to be AE square minus EF square, which is 13 square minus 12 square, or 169 minus 144, or 25. So AF is going to be square root of 25, which is 5. So I found my radius of this circle to be 5. Moving on, they want me to find BC and round it to the nearest whole number. So now I know AB is also a radii of the same circle. So this is also going to be 5. Again, I can use my theorem because this is also a 90-degree angle, to figure out that my BC square, or let's go with just BC. BC is going to be square root of 39 square minus 5 square. And when I did it on my calculator, I got this to be approximately 38.68. So to the nearest whole number, BC is also 39. So BC is 39, and so is CD, because BC and CD are equal. They are two tangents from the same exterior point. So EC is going to be ED plus DC. So this is 39. So this is going to be 12 plus 39 to give me 51. Okay, looking at the next problem together. I have to find X, the length of this segment X, which is the common tangents between the two circles. And the two circles are G and H. This is given to be 5, 4, and 3. So I know that the radius of circle G is 5 and that of circle H is 3. Now, to do this problem, my first step is I am going to draw a line parallel to, so I'm going to draw a line, let me call this point A, let me call a line AB, which is parallel to GH. So that is what I'm doing. I'm drawing a line AB that is parallel to GH. Okay, now I know that the length of GH is 5 plus 4 plus 3, which is 12. So now if I connect the points GA and HB, I have a quadrilateral. And in this quadrilateral, I can see the way I have drawn it, I have a rectangle. I know this is 90 degrees, and I also know this is 90 degrees. So if this is 90 degrees, then I'm going to call them angle 1 and angle 2. So angle 1 is equal to angle 2 is 90 degrees because my radii and the tangent lines are perpendicular to each other at the point of tangency. So then this angle 3 is also 90 degree because it is supplementary to angle 2. So angle 3 is 90 degrees also. So now I can see that let me call this point D. My triangle ABD is a right triangle. It is a right triangle. I'm looking at this triangle ABD, which is a right triangle. And so I know that BD, now because the radius of circle G is 5 and that of circle H is 3, I know BD is going to be BH minus HD, which is 5 minus 3, which is 2. So this length is 2. I also know AB is equal to GH is equal to 12. So AB is 12. Now I can easily find out X. X is going to be square root of 12 square minus 2 square. So it is square root of 144 minus 4, which is square root of 140. And when I find it to the nearest hundredth, okay, let's do this. To the nearest hundredth, square root of 140 is going to be 11.83. So the length X is 11.83. Okay, moving on. Actually, for today, I want to stop right here. And I have posted another resource on the resource 2 on the Google Doc. Go to that resource now and start looking at and start playing around with that resource, with that online activity that I've posted there. So for now, the new things, just to recap what we have learned today, is what is a tangent and what is a secant and the difference between the two. Also understand the difference between a secant and a chord. A chord is a line that is completely inside the circle and goes from one endpoint, and both the endpoints of the chord lie on the circle. A secant is different. A secant is just a line that passes through the circle and touches the circle in 2 points. Then we saw that the tangent and the radii of a circle meet each other at 90 degrees. They are always perpendicular to each other at the point of tangency. The next theorem we saw was that from any point on the exterior of a circle, any point on the exterior of a circle, when I draw 2 tangents to the circle, both the tangents are congruent to each other. So go ahead and play with the second resource now, and I will see you tomorrow, and we will continue this lesson, lesson 9. Okay, everyone, take care, stay safe and healthy. Bye.